Okay. So we are, the aim of this lecture is to give an algorithm to describe, to solve some kind of problem, but we need some backgrounds first. So we get back at talking about geodesics. We'll apply we'll use the Hamiltonian equation for geodesics, but we're talking about now about families of geodesics. So consider this setting. We have a Riemannian manifold, a point, and the exponential map from the tangent to the point to the manifold. So this is a local parameterization of your manifold. We fix a two-plane, so a two-dimensional plane inside the tangent space. We have a tangent space, we fix a two-dimensional plane. And we give polar, a vector space, so passing through the origin of your tangent space. And we fix polar coordinates on it, rho and theta. We define the vector v theta with rho 0 cos theta, rho 0 sin theta, okay. And we define the function from R times S1 to the manifold by ft theta equals the exponential at p of t v theta. We are doing this. We have our two-dimensional, we are inside the tangent space here, which is n-dimensional. We have our two-dimensional plane. We fix polar coordinates, so we have the r variable varying along the blue lines and the theta variable varying along the green lines, and we use the usual parameterization of these. This is just a rescaling of the radius, because instead of taking r, we are taking r0 times t, but it's the same thing. And we map this thing inside our manifold. Here we are inside the manifold M, which is n-dimensional. The origin goes to a point P. Your plane goes to some surface inside M. Now, by the properties of the exponential map, the blue lines go to geodesics. So the blue curves here are geodesics. The green lines go wherever they want to some closed curves around your point. I've drawn them like approximate ellipses because they are, but they are no geodesics or stuff like that. The only geodesics here are the straight line through P. Now, if you consider the two canonical vector fields, the d rho, the dr and the d theta vector fields, which are the radial direction and the circular direction, the rotating direction, they go to some vector fields, but the important thing is that the radial vector field will go to a vector field which follows the geodesic, so it will be a multiple of the velocity vector field of the geodesic. Whereas the angular component, so the rotating vector field, will end up into some other thing which describes, how does it relate to geodesics? You have, the blue lines are all the geodesics coming out from the point P on this surface. The angular variable describes how the geodesics is varying in the family. So this is a family of geodesics lying on a surface, and the angular parameter gives you the variation from a geodesic to the next one. So the associated vector field gives you the direction of variation of this family of geodesics. So we consider the vector fields dt and d theta, because t is the parameter of the geodesic, so dt and not dr is the right vector field to consider. So the push forward of dt, so the image through the differential of f of dt, is the vector field tangent to the geodesics, and it will be the velocity vector of the geodesics, because it is the derivative in t of the geodesics. Whereas the push forward of partial theta will be a vector field giving the variation. So you have the geodesics coming out from P, and you have the vector field that tells you how the geodesics are varying in this family. Now, we have two properties which are important. Obviously, this is the geodesic equation, because it's not a vector field tangent to the geodesic, it is the velocity of the geodesic. So this is nabla gamma dot equals 0. So this is the geodesic equation. And this is just the fact that t and theta are the parameters of a flat parameterization, are parameters in R times S1. So their commutator is 0, because that manifold is flat. Well, no, doesn't mean anything, because I mean, you can write it down, because they're independent. It's a product, so they're independent variables. So the related partial derivatives are do commute. And then when you apply the push forward, you get 0. Now, these two things are important because allow us to write down a differential equation for the field J, which describes, I mean, this is the differential equation for the field X. Solving this is the geodesic equation, and solving this gives you the differential equation for the field X, which we obtained from the Lagrangian. We also have the Hamiltonian one. So the field X is okay. Now, we would like to describe the field J. The fact that X and J commute implies that, first of all, that the xj minus the jx is 0. Because I mean, we are obviously using, okay, I never said it, but we're obviously using the Levi-Civita connection, so it's torsion-free. So for the torsion formula, you get that this would be equal to the commutator, but the commutator is 0. So this is 0. And then, from the this is the definition, well, from the definition of curvature. Curvature is how much the two partial derivatives, the two covariant derivatives do not commute. So the covariant derivatives in X and J, even taking into account how much the two vector fields do not commute. So this is the curvature. Now, we know that this is 0, and if we do a covariant derivative along a vector field which is null, we get 0. And we know that this is 0 because the the curves are geodesics. So you end up with the curvature being just this double covariant derivative, which is what is written here. So the first one is the definition of the derivative, taking into account that this is 0. And this term vanishes because this is the geodesic equation. So if you look at J along a geodesic, you get what? You get that the second, do you remember this symbol? I hope so. This is the covariant derivative along the curve, which is oh no, I've written here. So which is this expression? So it's the covariant derivative with respect to the vector field tangent, to the velocity vector of the curve. So x is the velocity vector of the curve. But we saw that nabla xj is equal to nabla jx because of the first relation, and this expression is equal to the curvature. Given a geodesic, a Jacobi vector field along gamma is a vector field j of t because it's just along the curve, such that the second derivative along the curve, so j second, is equal plus the curvature, the Riemann curvature tensor in j gamma dot is equal to 0. Notice that here you have the second derivative, but here you have a linear term. So this depends linearly, because this is the Riemann curvature, which is linear in every component. So this is the second derivative. This is an expression which is linear in J. These kind of vector fields are called Jacobi vector fields. Now, it's a second order differential equation, so you can fix the the value of j at the starting point of your curve and the value of j prime at the starting point of the curve. So you get that the space of Jacobi vector fields along a curve has dimension 2n. The variation vector fields for a family of geodesics are given by the conditions starting value equals 0 and starting vector equals some vector in the tangent space. So the variation vectors are just the n-dimensional subspace of Jacobi vector fields which start with 0 at the beginning. The Jacobi vector field at t is the differential of exp on the tangent space at P calculated at the point TV applied to the vector TW with V, the direction of your geodesics. So what we are saying here is that we have TPM, we have XP, we have M, the origin goes to P, the straight line here goes to some geodesic, and this point here is TV and goes to some point here, which is XP TV. Now, if we select some W here, which expresses the variation of the Jacobi vector field you want to build, so the variation vector field you want to build as a Jacobi vector field, we can consider the differential of XP at the point TV. So the differential of XP at the point TV is something that goes from the tangent at the point TV of TPM to the tangent at this point Q of M, where Q is this point here. Now, there is an easy, TPM is just Rn, so the tangent space to a point of Rn is just Rn in a canonical way. So we can identify this tangent space to just TPM, and so we can take W, or W inside of it, TW actually, because the identification is the multiplication by T. But anyway, we can understand this vector as a vector tangent not only to 0, but as a vector applied in TV in some way. And what we are saying here is that J of t is obtained as the differential of x at p at the point TV applied to TW. So in a way, Jacobi vector fields give you a control, give you a way to express the differential of the exponential map. Okay. A consequence of this is that we can write down the Taylor expansion of J of t, because t is just a real variable, which will be TW plus a term which is at least cubic in t. Why? Well, because okay, well, this part is obvious. I mean, this is just from the initial conditions, no? You get, whoa. You have J0 equals 0, J prime 0 equal W, and then you get the differential equation, which is this one. So, quite easily, these two imply what I just wrote. How about, well, the second derivative in 0? Quite obviously, I mean, remember that R is linear in J, so this is minus R of W plus little of T gamma dot, which is equal to what? To minus T gamma dot, well, plus or minus, who cares? Something like this. And this implies that the second derivative is 0. So, you get at least order 3. And this in turn implies that Jacobi vector fields approximate parallel transport. So if W is the parallel transport along of a vector small w along gamma, so the covariant derivative of W along with respect to gamma dot is 0, and W at gamma 0 is small w, then you can write this expression. So the value of w at gamma t is jt over t plus an error term which is small o, little o of t. The reason is easy. Consider j of t over t minus w at gamma t. And compare these, add and subtract the value at gamma 0. Now, obviously, this Jacobi vector field is the one given by these initial conditions. The notations were coherent all over the list. Is the Jacobi vector field given initially by the vector we want to parallel transport? Yeah, by the way, okay, divide this by t, because we want to show it that it's in small o of t. And now this is j of t minus wt over t squared plus this term. Now, well, not equal to, but okay, tends to 0. And if you remember, by definition of parallel transport, this tends to this. But this is just 0. And so you get that this whole term goes to 0. So this means that the parallel transport at gamma of w at gamma t is approximated by the Jacobi vector field starting with w as initial data over t. This means we can approximate parallel transport with Jacobi vector fields. How? Well, as follows. We compute the geodesic gamma, integrated the Hamiltonian equations, so we get just first order derivatives of the metric and the momenta. We compute another geodesic which starts not with direction v, but with direction v plus epsilon w. And we approximate jt with their difference over epsilon at time t. Why? Because this is exactly the approximate version of the differential of the exponential map. So we are approximating jt as a differential of the exponential map. And then we approximate the parallel transport of w with jt over t. In order for this, this works for small t's, obviously. So small t, it works. If you want to use this algorithm for a not infinitesimal parallel transport, you need to repeat this process every step, and so you want not to accumulate too much errors. That's why I was talking about second Runge-Kutta of order 2, so that if you're taking 1/n length, steps of length 1/n, the cumulative error of the Runge-Kutta method is 1/n squared. You get it n times, so you end up with 1/n. And so you still have your, and everything then is as little o of 1/n, which works as an approximation. Now, you need to integrate the geodesic equation, which are these ones. In particular, the second one, but also the first one comes into play. I mean, the first one is just the multiplication for the inverse metric, but the second one is actually a gradient of a covariant derivative. This is what I was talking before about the Runge-Kutta method. Then you approximate j of t plus h as the following quotient. Why? Well, this is the derivative of the exponential map at the point, if we did only one step, we wanted just the exponential map from gamma 0. But if we are doing it repeatedly, we have to update the exponential map at every step. We cannot keep using the geodesic coming out from gamma z, from the starting point. We use those to make one step, then we update both vector fields. We keep following the main geodesics, but then we use another auxiliary geodesic here to get the Jacobi vector field as a differential of the exponential map. We end up here, and we have at the new point our new parallel transport, and we go on like this. So every time we update the starting point for the auxiliary geodesics. And we obviously keep following the main geodesic we want to use for the parallel transport. Again, exp is computed just by, these two, if you look at these two are geodesics because they are linear in h. T is fixed and they're linear in h, so these two are geodesics. So we are just computing geodesics from the point gamma of t. One should be the continuation of our main geodesic, and the other is the auxiliary geodesic, which allows us to compute the Jacobi vector field. Now, the algorithm looks like this. We start from a natural number, a point x0, and v0 and w0 tangent vectors at 0. We want to compute the geodesic with direction v and transport w. First of all, we calculate the momentum, so the conjugate momentum variable for our Hamiltonian equations, which is just, computing the metric and doing the multiplications. Now, we compute the next point along the main geodesic. So we start from xk and we compute we solve the geodesic system with vector vk. Then we compute the next point of the auxiliary geodesic, which goes out from xk. No, from xk. Well, anyway. With direction wk. So wk is the parallel transport up to that point. Now, the first idea would be to take these as now the step is 1, so the time is 1, so dividing by time is just dividing by 1. So one would consider this as the Jacobi vector field, and so these as the approximation of the parallel transport. However, we can do something to reduce the possible errors, computational errors we've done, which is the following. We define a new vector, wk plus 1, which is a combination of this increment and the tangent vector to the geodesic. So we also compute the parallel transport of V, which is just given from the Hamiltonian equations. So we combine our estimation for the Jacobi vector field with the tangent vector to geodesic. Why? Because we want to so these two quantities are constant, meaning that these quantities should be preserved along the flow, along the geodesic. Nothing guarantees that our W hat has these properties, but we can just, I mean, if you remember the picture with the plane we used in the previous, in this lecture, if you remember the picture with the plane, you have a basis which is just the variation direction and the velocity of the geodesic. So if things didn't go too much astray, you can correct your W hat with the velocity of the geodesic, which is the other element in that plane in the tangent space. So you actually choose lambda and k so that these equations hold. It means solving a linear system, two linear systems. One, well, whatever, some linear systems. And you get your parallel transportation up to the step WK. Sorry. This is not too heavy to compute. I mean, these are all Runge-Kutta methods to compute geodesics. It's not too bad. This is just a difference. I mean, it's the easy part. The real problems are here when you compute the. I mean, you also want to revert to invert the metric matrix, and you want to solve linear systems. So these operations are heavy ones. Usually, you hope to have a closed form for the metric and the inverse metric, and you are left with solving a linear system, which is the only really, I mean, computationally interesting step in this algorithm, but it's not, luckily, it's not too heavy. I mean, there are other algorithms for computing parallel transport which have weird name like the pole ladder algorithm and stuff like that. But this is, I mean, this is the, in a way, more robust one and newest one. From not too many years ago, like 4 or 5 years ago. Now, an interesting application of this technique is the study of time series of images, like medical images. So you have scans of MRIs of a brain with some degenerative disease, and you want to trace the evolution of the disease. And you want to compare different evolutions, or you want to translate one evolution to another patient, and stuff like that. Obviously, this is not the only way you could apply all this machinery, but it's one of the applications it got. I mean, mainly, the main application it got. The people who developed the previous algorithm were working in images time series and stuff like that. So what's the setting? You have images, VI, so that there are images of the same object taken at different times with equal or unequal time increments, And I mean, depending on the kind of study you are conducting, this could be like frames of a video, so the time intervals are fractions of a second, or this could be medical exams performed through time. So maybe the distances in time are years. Okay, that depends. Also depends on the time scale of the phenomenon you're looking at. So we want to analyze the changes between one image and the other. Obviously, we are in a very safe setting, so the images are all centered in the same way. I mean, it's a medical exam. It's not a picture taken by a guy passing on the other side of the street. So the position of the object in the frame is always the same. There are some standards, there are some calibrations and stuff like that. So it's a very safe environment in which to analyze differences between images, because the differences you see are likely to be differences in the object and not just in the way you took the picture, roughly speaking. One way to analyze the differences is to determine the best diffeomorphism that transforms one image into the next. So the best transformation of the plane that takes the first image and sends it to the second image. Now, the problem is to quantify the word best. If, okay, these pictures. If you try and give a precise meaning to the word best diffeomorphism, you end up writing down an energy function, some distance between, some norm on the diffeomorphisms, which ends up being some distance between diffeomorphisms. Now, what's missing here is the fact that you also will be likely to want to discretize diffeomorphisms. So you're not writing down equations in X and Y. You are prescribing, I mean, you are, okay. The usual way is the following. You relate diffeomorphism with the flow of a vector field at t equal 1. Then you discretize the vector field. So you have your image, and you just take any grid decomposition, select a point which may or may not be the center in each square of the grid. It's not always the center also because you want things to evolve, and you fix for each point a vector, etc. Now, a nice way to produce meaningful discretizations of vector field is to write down your vectors as in terms of the momenta, because then you will be computing the, you will be using the Hamiltonian equation, so you will be working with the conjugate momenta instead of the velocity vector fields. So the usual thing is to use, instead of giving the vector field, you give the dual, and where you lower the index using the matrix, the metric. so you also write down the metric. And the metric is usually something which is Gaussian, because you want to, you would like to measure small deformations of your image. You're not interested in large deformation. I mean, if you're taking a time series of images of an object, you hope that these describe an evolution, as smooth as possible evolution. If the image changes dramatically, there's something wrong. So what you're interested in is a small deformation of your image. So the best choice of metric to compare your differentialism is something Gaussian, which will be giving a lot of importance on the variation of nearby vector fields. So from the metric on the metric on the differentialism is a norm on these vector fields. So the norm of these vector fields is given by giving much more importance at points nearby one of those instead of points on the other side of the grid, for example. So this is what is behind this whole thing. And usually you end up writing down things that are already studied, which are called reproducing kernel Hilbert spaces. But anyway, so if you write down everything, you end up with something which luckily is already studied in another part of mathematics, which is the reproducing kernel Hilbert spaces. But anyway, so you take this distance on a space of differentialism, which ends up being a scalar product on the space of discretized vector fields, which actually is a scalar product on the space of discretized momenta in the Hamiltonian way. And now you do things like that. So you have these dots are your time series. You approximate them with the curve, so sort of geodesic regression. And then you have another image for another patient, for example. What can you do is estimate the geodesic path from your curve, the patient A curve, to the image of patient B. So this dotted line is geodesic. This is just the velocity vector of this curve, which is not a geodesic in principle. Now what do? You parallel transport the red, orange vector to this point, and you build the new patient curve. So what is this? This is the forecasting for patient 2 given the time series of patient 1. So in general, this allows to reproduce the evolution starting from a different image. Now, this is obviously interesting because if for one patient you have landmarks and you can study the evolution of, you have already studied the evolution of a disease, for example, you can do the same for another patient. And this approach with curves lets you separate the time dependence and the space dependence. So you can have a curve which is the same but traveled with a different speed, so reparameterized. You can also take this into account because the evolution of a disease or of any phenomenon can be different in time, but with the same steps in a way, just traveled in different times. So this also helps in this way. And this is actually quite a new approach. It was in a PhD thesis from 2020. So in papers from 2018 and 2019, because it was a French PhD thesis, so the papers were published before the thesis. And okay, I think this is enough on the subject.